Une fois formées, les étoiles brillent.
Once formed, the stars shine, thanks to the nuclear reactions in their core. The energy produced is transported to the surface, which in turn warms up and remits black body radiation. We will see in what follows how one can classify the stars depending on their luminosity and on their color, which is actually depending on the black body temperature. This video describes the stellar spectral classification and introduces an essential tool for astrophysicists, the Hertzsprung-Russell diagram. Let us now see how to classify the stars. The main difference between stars is their temperature. This temperature determines the colors of the stars. The stellar classification is therefore a spectral classification, mainly linked to the surface color, the surface temperature of the stars. Here are all known kinds of stars. There are 7 different spectral types, each with its temperature. Here is, for example, an extremely blue star with a black body radiation at 40,000 Kelvin. So an extremely hot star, among the hottest that exist. As such, it has a much higher flux in the blue part of the spectrum. Here is the blue, and here is the red. Conversely, if we take a cold star such as this one, with a black body temperature of more or less 3000 Kelvin, the spectrum is much redder. There is more flux on the red than on the blue side of the spectrum. Between the two, we have stars similar to the Sun. The Sun, with a temperature of about 5,780 kelvins, is a star with a mainly yellow spectrum. To measure the color of stars, we use color indices. We usually use the B and V filters in the optical domain, and then we measure the slope of the spectrum as a function of the color index. Each time the temperature of a star changes, we have a change in the slope of the spectrum, and also several spectral lines, such as these ones. We can see the hydrogen spectral lines, for example, as well as molecular bands appearing in colder stars. Depending on a star's temperature, its color changes and the absorption or line emission lines in its spectrum also change. How do we measure the slope of a spectrum? We have already seen this. I take this star with the blue spectrum as an example. If I measure the flux at the center of the B filter bandwidth and the flux at the center of the V filter bandwidth, I can measure the slope of the spectrum thanks to these two values. We have then some slope, which is blue since there is more flux in the blue than in the red domain. If I now take the green star on this figure, I have a first measure in the B filter and a second one in the V filter, and I get then a much more horizontal spectrum slope. The star is thus less blue, simply because its temperature is lower than the previous star. The BV index is therefore an indicator of the spectral type, and it is this index that will appear later in the color magnitude diagram. If B minus V is large, then we have a red star. And if B minus V is small, then we have a rather blue star. The spectral classification is based, as the name suggests, on spectra. There are 7 spectral classes at the basis of the Harvard classification. In the Harvard system, we have spectral types named as O, B, A, F, G, K, and M. We have 7 letters to indicate several spectral types. From one side of the scale to the other, the temperature decreases. We typically go from 40,000 degrees here down to 3,000 Kelvin here. Here are a few examples of spectral types. O, B, and A, the first 3 spectral types, corresponding to the following temperatures. This is the range in temperatures. Each spectral type has different features. In each case, we have hydrogen here. But depending on the temperature, the spectral lines are stronger or weaker. In very hot stars, we also have helium lines, and here as well. And here, there isn't any helium anymore. If the star is extremely hot, we can also see lines of species of a much higher ionization energy, such as carbon or oxygen. The depth at which the lines form depends on two things: the rate, the number of ionizing photons emitted by the star, and the recombination rate. For example, in the case of hydrogen, the recombination of photons and electrons. In the case of an extremely hot star, the rate of emitted photons, the flux of ionizing photons, is much higher than the photon-electron recombination rate per unit of time. This means that, contrarily to what one may think, the hydrogen spectral lines are formed less deep than for a colder star, where there are much more atoms, so more electron-proton pairs, able to reabsorb light and create the hydrogen spectral lines. Each spectral type has, of course, its own temperature. When we go toward the red domain, toward colder temperatures, the black body peak is translated toward the red domain. Here the peak is at 4,000 angstrom. Here it is shorter than 4,000 angstrom. And finally, the peak here is far outside of the diagram. Stars become, therefore, redder and redder when going towards the M spectral type. We have here O, B, and A stars. Let us now consider the other spectral types, F, G, K, and M. In this case, the temperatures are in the following range. As said before, there are 7 spectral classes. And here are the 4 last ones: O, B, A, F, G, K, and M. We see the black body peak moving toward the red domain as temperature decreases. We also witness other features. For example, there are here some metallic lines, such as calcium lines. They also appear here. The Sun is, by the way, a star in the temperature range of 5,000 to 6,000 Kelvin, therefore a G star with 5,780 Kelvin. As the surface temperature of the star gets colder, we notice molecular bands. Molecules are therefore broken at high temperatures. When the temperature of a star decreases, molecules will absorb light and produce wide lines. They are actually composed of a great number of very narrow lines, which we cannot distinguish due to the limited instrumental resolution. We see here several bunches, each made of a large number of molecular lines. Hence, stars with cold temperature feature spectral lines typical of molecules. There are 7 spectral classes, and there are also 10 subclasses. We have 10 divisions between 2 letters, ranging from 0 to 9. In addition, there are 7 luminosity classes. Reflecting essentially the radius of the stars. They are the 1A and 1B luminosities, 2, 3, up to 6 Roman numerals. We will talk about their meaning later. For example, the Sun is a G2V star. G for the temperature, and 2 to split the temperature interval, into 10 finer intervals. The Sun is thus at 5,780 Kelvin. 5, Roman numeral, is the luminosity class of the Sun, which corresponds to the class of 80% of stars. We have just seen that stars can be classified in terms of luminosity and temperature, the latter being at the origin of their color. It is, as such, logical to build a diagram showing both quantities and corresponding stars. We are going to do this for the Omega Centauri globular cluster. We first sort the stars by color, moving blue stars to the left side and the red stars to the right side of the diagram. This actually corresponds by sorting them by temperature, with blue hot stars to the left and red cold ones to the right. It simply illustrates Wien's displacement law. For a black-body spectrum, we now sort them by luminosity and put the faint stars with a high magnitude at the bottom of the diagram, and the bright stars with small or even negative magnitudes for the brightest at the top of the diagram. The resulting diagram is called the Hertzsprung-Russell diagram, or HR diagram. As you notice, stars are not randomly distributed across the diagram, but instead follow a well-defined sequence, which we will now see. What kind of stars are on the diagram? Where are they located? And what other physical parameters? Here is a color magnitude diagram, a Hertzsprung-Russell diagram, for 22,000 stars of our Milky Way. We have 4 axes on this diagram. We see at the top the spectral classes, O, B, A, F, G, K, and M, ranging from the hottest temperatures, around 30 to 40,000 Kelvin, to the lowest, about 3,000 Kelvin. We will draw the different axes. We have at the bottom an axis representing the color BV, for example, with the lowest values to the left and the highest to the right. Red colors are on this side, and blue ones are here. A blue color means a high black body temperature. Therefore, the top axis, showing the temperature, varies in the opposite direction to the bottom axis. We have here temperature increasing in this direction. The luminosity axis increases in this direction. Here's the luminosity of stars in the units of solar luminosity. In the opposite side, we have the axis of absolute magnitudes, which increases downwards. The absolute magnitude is the apparent magnitude a star would have if it was located at a distance of 10 parsecs. The diagram shows several classes of luminosity. We have here very big and bright stars, hypergiant and supergiant stars. Here are the bright giants, the giants, and the subgiants. 80% of stars are actually on this sequence called the main sequence. Stars burn their hydrogen into helium during all their life on this sequence. It is hence a mass sequence called the main sequence. We have at last the sequence of dwarfs. White dwarfs are located in this area of the color magnitude diagram. We have 22,000 stars of the Milky Way. 80% of the stars are located here, and the stars which become giants are in this area of the color magnitude diagram. We can also draw isoradius contours on the diagram. We already said that the higher we are on the diagram, the bigger the stars. To understand this, remember that the luminosity of a star depends on its surface. R is the radius of a star, and it is multiplied by sigma T4. This could be rewritten in terms of solar units. We have L over the solar luminosity. And here remains the squared ratio of R over the solar radius. Since both 4 pi and sigma vanished, the same holds for the temperature if one divides by the corresponding solar quantity. We have such a relation that we can turn into a logarithmic one. I do not rewrite each time the solar units. We obtain that the logarithm of L is twice the logarithm of R, plus 4 times the logarithm of the temperature, where, of course, everything is written in solar units. solar luminosities, solar radii, and solar temperatures. If r is constant, we have the equation of a straight line. In a log-log scale, a function which behaves like y equals ax plus b, where y is the logarithm of L. B is twice the logarithm of r, which stays constant, since r has a fixed value. And here is x, with the constant a in front. This is simply the equation of a straight line in the HR diagram. In the color magnitude diagram, this straight line is drawn here, and here is the position of the sun. Now let us change the value of the radius. Here we have one solar radius, one solar luminosity, and one solar temperature. When r changes, the value of the parameter b changes as well. Therefore, the y-intercept point of this line changes. We are translating our lines towards the top or the bottom of the diagram. By the way, since we are talking about stellar radius in the main sequence, along this straight line, typical radii range between 0.1 solar radii up to 15 solar radii. It is not the same thing for giant or hypergiant stars. If we consider the whole range of radii for all stars, then the range is obviously much wider, and we can reach up to 1,000 solar radii for hypergiant stars. On the other hand, dwarf stars can have 1/100th of the solar radius. The range of radii, therefore, spans 5 orders of magnitude, from one extreme radius to the other extreme. A note on the effect of interstellar absorption in the color magnitude diagram. Remember that the observed magnitude of an object is the intrinsic magnitude, plus some absorption. The positive sign is because, after absorption, a star appears less bright than its real magnitude, so the magnitude will be larger, and for that reason we add a positive quantity. We saw that this absorption coefficient depends on the color. The absorption does not only cause an increase in magnitude, but also makes the stars appear redder, as we saw in the chapter on the interstellar medium. If we take the example of this diagram, with a stellar population corresponding to a star cluster, this diagram shows the Milky Way, but let us suppose that we observe a homogeneous stellar population, a star cluster, that we observe from Earth, with dust clouds in between. Then the diagram will be shifted downwards. The sequence is shifted downwards, but also reddens, which means that we have a reddening vector in the direction of increasing BV. In conclusion, the diagram is shifted along a diagonal reddening vector. We therefore have to be cautious on the conclusions of the study of stellar population when we obtain such a color magnitude or HR diagram, because it can be affected by reddening on the line of sight of the star we are observing. A last word on the radius of stars. We said that we can draw isoradius straight lines in the color magnitude diagram. We will see here that the radius cannot be directly measured. To understand this, we can look at the flux received on Earth from a star at a distance d. And compute this flux as a function of the flux on the surface of the star with a radius r, the luminous flux. The two fluxes relate as follow. The observed flux is the intrinsic flux times the surface of the star times 1 over a sphere of radius d. We then deduce that F equals F r divided by 2 square. RD is simply the angular radius of the star, the subtended radius of the star at some distance. We have here the radius of a star, the angle A, and the distance d. Considering a hypergiant star at a distance of 200 parsec, a very close star with a radius of 1,000 solar radii, we get that A is roughly equal to 0.02 arcsecond. 0.02 arcsecond is approximately half the size of the smallest visible detail by current telescopes. It is therefore totally impossible to observe the surface of another star than the Sun. The Sun is the only star on which we see surface features. The color magnitude diagram is an incomparable precious tool to characterize stellar populations from the simple measurement of color and luminosity, the color being linked to the temperature. Be attentive, however, that the diagram is valid only if all the objects in it are at the same distance from us. In other words, if we show the diagram in terms of luminosity or in terms of absolute magnitudes, namely the magnitude brought to the arbitrary distance of 10 parsecs. In the next video, we will see how the stars move in the diagram in the course of their life. It is a whole domain of astrophysics, the study of stellar evolution.